Okay, what do we have going on here? Sine of x over what? 3x over 1, multiply top and bottom by 1/3. Yep, that's a 1/3. You were right. X over, well, that's a terrible looking 1/3, but so I'll try to make it look a little better. There we go. So what's the period? 2 pi over 3, okay. Right, the original period was 2 pi, but we shrunk it down by 1/3. And what's the amplitude? Okay, so whether you chose a color or a dotted line, we should have something that, let's see, HK is on the wave. Whoa, 2 pi over 3 units later, I have to be starting over again? Wow, that's not a big one, right? So something like this. Just for fun, we'll do another one over here. And we'll do one more the other direction. Okay. So now we want to graph the cosecant. It's the same exact stretch and shrink, but it's cosecant that we're graphing. So either use a different color or a solid line for this part. So I'll choose a different color. So I'm going to be doing this one in red. I guess I should have circled the other one in blue, since that's what I did it with. Well, lock it in. So I'm doing that one in blue, and I'm doing the next one in red. What happens at every single x-intercept? What? It's undefined, which creates asymptotes. Here, I'll do green for my asymptotes.
What did you say creates the asymptotes?
The x-intercept of that sine wave, because those are zeros, and if you flip it over, you get an undefined value. Okay? What? Oh, student made it for me, and they asked me to wear it. So now maybe I need to back up a little bit. What's going on between each one of these asymptotes? What do I need to do? So what do I do between any of the asymptotes? How do I graph the cosecant? You've got to basically do what looks like a parabolic shape between the asymptotes. Now, it's not a parabolic shape. It's probably a little more flat than I'm drawing it, but this kind of gets you the idea. And so, in between every one of these asymptotes, we have one of these shapes. Because the reciprocals, you're taking the reciprocal of every single one of those values. And when we do the reciprocal, we end up with these different shapes. So the original shapes, the blue ones, are not there. But I used the original sine function to help me draw the cosecant function. We can ask you things like domain. What's the domain of this function? All reals except what? Okay, so every one of these, you got 0, pi over 3, 2 pi over 3, pi, 4 pi over 3, negative pi over 3, negative 2 pi over 3. So that sounds like integer multiples of what? Pi over 3, right? All real numbers except integer multiples of pi over 3. Whether it's 1 pi over 3 or negative 17 pi over 3. What's the range? Yes? Well, I better look at this. Oh, yeah. All reals minus, integer multiples of pi over 3. Yeah, I'll take that. Yeah, he was just asking if we could write this domain in a format like this. All reals minus, and then in these brackets, all that stuff. Integer multiples of pi over 3. Yeah, that'll work. Okay, so how about that range? Come on, smash it all onto the y-axis. If you crushed the whole graph onto the y-axis, how much of the y-axis would get covered? There is no way that all of it would get covered, folks. I mean, think about this. There is a huge gap in the middle where there's nothing. Okay, so negative infinity all the way to what? Negative 2. So there's a parenthesis here. What about on the negative 2? Bracket. Union 2 to infinity. Yeah, you can't include those values in the middle. There's nothing there. They all just want to say, all reals. I'm like, come on, look. Okay, here's the next one. So your first one is whatever color you want to start with. I'll choose blue to start with. Whoa. All right, or you could do a dotted line if you want for your cosine function. We can put it in fireproof form. Y over 3 equals cosine of what? X over 2, right? So what's my amplitude? 3. What's my period? 4 pi, right? We doubled it, right? We started with the original period and stretched it by a factor of 2. HK is still here. Between, down at the bottom. Graph a couple of these. You get the idea. Hopefully you were able to do the same type of thing quickly because you know how to graph cosine functions. HK sits under the max, and you can use the amplitude to go up and find the first point, and then the period to find the next point, and all that good stuff. Okay? Same thing we've done before. So now I want to graph the one at the bottom of the screen, 3 secant 1/2 x. What happens at every one of the x-intercepts of the cosine way? Undefined, right? So you get one of those vertical asymptotes. So whatever color, question? Always, because that 0, when you flip it over, becomes an undefined value. That's why I like to graph the cosine or the sine quickly, and then I go from there to find the real graph of the secant or cosecant. So what's going to happen in between every one of those asymptotes? The same thing we had going on before, right? Over and over and over and over. I know, it's pretty cool. So the blue one isn't there. There's your picture of your secant. What's your domain? All reals except here I got pi, 3 pi, negative 3 pi. But notice I'm missing things like 2 pi and 4 pi and 0. Odd integer multiples of pi. How about that range? No, we're not having a party on Friday. Oh, Pi Day. Sorry, I thought you said Friday. Okay. We can, yes. You can bring in pi. Okay. Yep. You should. If you bring stuff, we can have. Yeah, most of you should bring 2 pi, because if you only bring 1 pi, that's like 180 degrees, right? Oh, that's a classic. Now, you know one of my favorite things to see on a quiz or test? Okay, you know, it says at the top of every quiz and test, name, period, you know, that kind of thing. Maybe date, I don't know, but definitely says name and period. So when it hits period, somebody writes 2 pi. I love that, man. Somebody's thinking, man. Way outside the wave, you know what I'm saying? Okay. Okay, what's our range? We didn't get that one. Yeah, what do you think? Yep, there we go. Negative infinity. All the way up to negative 3. Put the bracket there and a parenthesis there. Union. Wow, I didn't leave myself enough room. Bracket 3 to infinity. Parenthesis. So, one of our retired math teachers, Mrs. Gamble, was listening to the radio this morning, and the question of the day on the radio was, "What's the cosine of 60 degrees?" Of course, no, I didn't. I didn't hear this at all. I wasn't listening. I don't know. I don't think she did. But the first caller guessed 25. Well, what's the highest cosine there possibly is? Oh! Ouch! Take the dagger out right now. Okay, think about the cosine wave. What's 1, right? So I texted back to Mrs. Gamble and I told her unit circle amateurs. Seriously.
Did she call in?
I don't know that she had the time to call in, but, you know, math teachers around the world. What?
Could you flex? How fast?
Could I flex with a unit circle? Maybe only on a flex day, I'm not sure.
Wait, how fast can you be?
No, I don't. I have a hard time cracking him. You know, he does not like my humor, right? Am I right? I'm getting there? All right. Someday I'll work my way up to the UK standards. Okay. So tangent 1/2. Let's do this one real quick. Tangent, all right, that's x over 2. So what's the period of this one going to be? Remember, what is the period of a normal tangent function? It's different than cosine and sine, remember? Remember, it's pi, and then we multiply by a, not 2 pi. So if we have horizontally stretched this by 2, what is the period of this? 2 pi, right? So if you took a normal tangent function which has asymptotes like right here and right here at pi over 2 and negative pi over 2, and you doubled it, where are they going to land? Come on. Pi over 2. If I double pi over 2, what do I get? I get pi. And then I get negative pi. So I guess my question to you is, oops, I want to get rid of the green ones. Come on. So my question, where would the next one be after 1 pi? It can't be 2 pi because the period's 2 pi. Oh, it has to be. Wouldn't the distance between the asymptotes have to be the same? Okay, thank you. Okay, so we know that those are the asymptotes for this tangent function. And we know the basic shape, it has to do these things. Okay, so I graphed this one in purple. I know that's a... So now we need to do the cotangent, right? I'm going to do that one in red, cotangent. Okie dokie. So what happens at every one of those the x-intercepts? Asymptote. What happens at every one of the purple asymptotes, the old asymptotes? Exactly. That is where that center line of each one of those is. Okay. So I'm going to try to get rid of all my purple. Might take me a second, folks. Get rid of my purple. Be careful. Yeah. Gotta get rid of my purple. Why is what? Okay. Now, when you take the reciprocal of the values, like when you take you're going to end up with shapes that end up looking like this. Okay? So, say that again. Negative tan would, if you're trying to talk about if we started with negative tan and then we switched it to cotangent, yeah, it would be reversed. So the negative cotangent kind of looks like a tangent. Okay, so I just thought I would, maybe we go domain and range on this. Oh yeah, let's do this. Domain. All reals except 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, negative 2 pi, negative 4 pi, negative 6 pi. One way to say it would be even multiples of what? Of pi. But there's another way we could say it. We could also say it all multiples of 2 pi. I guess even integer multiples. We've been using the word integer for a good reason. Okay. All integer multiples of 2 pi. Cool sweater. I thought it had cotangent waves on it for a second. But then they disappeared, so I was totally disappointed. Yeah, that was really enlightening. Oh my goodness, I thought that was a good one. Enlightening? There was light all over her because it was shining from the projector. All right, never mind. I'm sure that just made me fall off the UK charts there, man. With my... Okay, yes. Okay, range. How about that range on that cotangent function? Take a look at it. Give me the range. Not you, Miss Johnson. Somebody else. Nope. Not going to let it happen. You're going to go with all reals? You would be right this time. That's right. Every single y value in the universe. You smash it all onto the y-axis, you'd cover everything. Right? There's no stopping that one. The big all reals, you know. If I was a superhero, that would be the sign they would shine up in the sky to get me to come out of, you know, the all real cave. Because it was just weighing me down, man. It was too heavy. Okay.